that. Ah, there we are. Now it's recording. Great. So today is going to be lecture 14, and it's going to be the third part in our series on estimation theory, specifically emphasizing batch estimation today. So let me go ahead and share my screen, and we'll just quickly talk about what we learned last time. So we're used to seeing problems that look like this. Y with a little squiggle over it, meaning it's a noisy vector of measurements, is equal to h times x, where x is our state, and then h is the measurement sensitivity matrix, which kind of describes the relationship between our measurement and our state. Now, in general, our estimation problems are going to be nonlinear, right? Right now, we're focusing on a specific set of linear estimation problems that look like y equals hx. And then we model the noise, because these are noisy measurements, as a vector of random variables, so a random vector, using the Greek letter nu. And so this is kind of our quintessential linear estimation problem. And over the course of estimation theory part 1, which was kind of the shortened lecture 12, we talked about the kind of simplest way to solve problems of this type, which is called least squares. Lecture 13, we talked about weighted least squares, which is like the evolution of least squares, and then maximum likelihood estimation, which is one step even beyond that. And this is kind of a really fancy way of solving these sorts of problems. And then finally, we got into discussing something called batch estimation, which is what we're really going to be lingering on today, right? So in general, it's very, very rare for all of your measurements to become available at the same time. That's not how it typically happens. We don't have at one snapshot 8 measurements come in and we just feed them into the computer, right? Typically what happens is we have measurements over a period of time, and that leads to 2 kind of strategies for how to deal with that. One of those is to have a computer running, constantly updating what it thinks its state is, and then when a new measurement comes in, taking that information and putting it into the system and kind of, synthesizing some new state estimate whenever a new measurement becomes available. All of that is called sequential estimation, and it requires a computer to be running all the time. And that is Kalman filtering is kind of when people think of sequential estimation, they typically think of a Kalman filter, an extended Kalman filter, or, an unscented Kalman filter, or a multiplicative extended Kalman filter. But they all have the name Kalman in there somewhere. Kalman filters, for example, is going to be what flies on the Orion spacecraft, that sort of thing. And so think, guidance computer running on the spacecraft all the time, right? That's Kalman filtering. We have a whole unit on that later in this class. But the other topic, which I want to discuss, is called batch estimation, which is something essentially kind of instead of handling the measurements as they come in, we're going to save them up and then process them all at once. We're trying to take these equations, these measurements that are spread out over time, and turn them back into y equals hx, right? And so what we really want is y equals hx. That's a linear system that we know how to solve. The problem is we can't, each measurement is not a measurement of the same state. It's a measurement of the same system. Let's say you have a spacecraft in orbit, you want to track its position and velocity. The thing is, if you have its position and velocity now, you know its position and velocity later. So if you are measuring its position and velocity later, you can actually, there's mathematical ways to relate a measurement of the future state to a past state, or a past state to a future state. And the way that we do this in matrix math is using what we call the state transition matrix, which is this capital phi or phi, depending on your pronunciation. And we just introduced this at the end of the last lecture, and then we kind of ran out of time. And so that's what we're going to really focus on today is the state transition matrix. I want to demystify it and get this idea across that, okay, there's a matrix which describes the mapping between the state as it was to the state as it is. And that matrix, used in conjunction with our measurement sensitivity matrix, allows us to take measurements over time and estimate the state at a single time. And that could be in the future, that could be in the middle of the measurements, it could be before any of the measurements are taken. But ultimately, we're twisting ourselves up into a pretzel doing this fun math to try to get back to y equals hx. That's really what we're after, y equals hx. So once we have y equals hx, we've practiced how to solve problems like that. Right, so that's the idea behind batch estimation. So I'm going to resume from where we left off. Any questions on batch estimation so far? Okay, so let's see here. I'm going to add, let's see, there's 1 or 2 little bits. So I have right at the top of my next page of notes, I have a few things that we didn't get to. And I'm just going to say, we'll start like this. Okay. A few words on batch estimation. So a few. These are just some notes that I forgot to give you last lecture. So we're going to start off with these. A few words on batch estimation. Number one, this technique combines all available data past, present, and future to estimate the state at sometime tk. Tk can be past, present, or future of when the measurements are. Now, we are also linearizing. You might have picked up on this. We assume that the measurements at play, or sorry, not the measurements, the dynamics at play, apologies. The dynamics at play can be safely linearized. Oops. Sorry, I'm still calibrating myself here. Can be safely linearized over the timescales between MES. Right. So what we're saying here is you might have noticed that this state transition matrix phi, we are essentially linearizing our state. So we're saying, okay, our state, which could be position and velocity, could be something else. Our state phi, if you just multiply it by this matrix, gives us our future state. That is a linear system by definition. And most systems, in fact, almost all systems are nonlinear. The two-body equations are nonlinear. However, we can linearize them. We can create this phi matrix over sufficiently short time spans. We're just hoping that we can get away with it. So whenever we linearize, which is a lot in engineering, we now have to kind of play in the region around the point where we linearized. And we know that if we stray too far, things start to fall off the rails. And we're used to that by now. All right. So now a quick word on observability, and then we'll get into an example which should be helpful for your homework. So observability. Those of you that have taken systems analysis techniques will have heard this already. So observability has to do with our measurement sensitivity matrix, actually. So we'll see this in a minute. Observability is one of the most useful and fundamental concepts in estimation theory. It's ultimately trying to answer the question, can we solve for X? Like, is the problem well conditioned such that we can actually solve it for a unique solution? That is not always true. Sometimes you'll have, a singular matrix where you can't solve for X, that sort of thing. So observability is one of the most useful and fundamental concepts in estimation theory. A system is observable if you can uniquely is important, determine the state from the available measurements. And so observability depends on how you set up the problem. So it depends on measurement geometry, problem formulation, assumptions, and choice of states. As we'll see, what states we're after is somewhat up to you, and it's possible to shoot yourself in the foot by picking the wrong states to estimate. So we will focus on observability of linear systems. So let's just kind of take an example that we can think about for ourselves. Consider the case that you have many range estimates to a spacecraft over time. And you're trying to batch estimate its position. So you know the range from you to the spacecraft at time t1, and then you know it at some time t2, and then you know it at some time t3, and so on and so forth. How many of those range measurements is enough to uniquely determine the position of the spacecraft? So we can think in terms of degrees of freedom, and so the spacecraft position has 3 degrees of freedom, and maybe its velocity has another 3 degrees of freedom. So maybe we have 6 states that we're trying to estimate. And let's say that I have 6 range measurements over time. Is that enough to kind of synthesize one single measurement of the whole state? Well, the answer is an infinite number of those measurements would still not be enough to estimate the state because we've actually set up the problem in a way that it's unsolvable, right? In this case, you're only ever looking at one component of spacecraft position. So as it drifts away from you, you have its range, and then you have another range, and then you have another range. But just think, there's so many ways for it to be moving that would give those measurements, essentially. So it actually doesn't matter how many measurements you have. This problem is unobservable. Now, if you have range estimates from different ground stations, right, then it's different. Now what you're doing is you're separating your baseline out. You can actually look at your range from many different locations. It becomes a trilateration problem. All of a sudden it's observable. But assuming it's the same ground station, just measuring range again and again and again and again and again, that will never be enough information to recover the full state because there are many ways. So we're going to prove mathematically that that's the case, or show how you would prove mathematically that that's the case. But you can also just kind of think about it and say, well, I'm only ever getting range from one ground station. That only ever gives one component of the position. Now, I might be able to estimate my range rate if I have multiple of those over time. I might be able to get some other information, but it's never going to be enough to get the full state because you don't know, and there's 2 other components of its position that you don't have, right? So that's just kind of a thought experiment to run through the idea of observability. There's situations where you might have more equations or more measurements than you know what to do with, and it still won't be enough, right? So recall, and I might take a second here. Consider the case that you have many range estimates to a spacecraft over time from the same ground station. That might not have been obvious. Just to be clear. So recall the maximum likelihood estimation solution. X equals H transpose R inverse H transpose R inverse Y. Right? For this to have a solution, notice there's a matrix inverse in there. H transpose R inverse H, which is a square matrix, must be invertible. Okay. Now we know R, which is the measurement covariance matrix, is a square diagonal matrix. It's actually symmetric, positive, semi-definite. Per the definition of that matrix, it is symmetric, positive, semi-definite. And in my experience, it's usually a diagonal matrix. That means, by definition, that it is full rank and therefore invertible. So that is not the weakest link in the chain. H, on the other hand, must have rank n, where n is the number of states. Now recall that H is a M by N matrix, where M, Mike, is the number of measurements, and N, November, is the number of states. This means that H must be what we call full column rank. So essentially, the punchline is here. The test for observability for a linear system is this. Are the columns of H linearly independent? And so we're going to see an example of this coming up later in today's lecture, but you can think back to our discussion of gimbal lock from several lectures ago in attitude representations, right? We start talking about measuring the Euler angles or measuring the roll, pitch, and yaw, describing the rotation from the inertial frame to the spacecraft frame. If you have a physical device consisting of these interlocking rings that tell us that attitude, and if the axes of two of those rings line up, not only is the physical device now stuck, such that you need to get in there with your hand and unstick it, also you've reached a situation where the matrix, which describes that rotation, has a singularity. And when that matrix is singular, it's uninvertible. And so we get to this kind of common, like here we see this again, singular matrix, the matrix math becomes unsolvable. It's an uninvertible matrix, can't move forward. And so this happens when the columns when we lose column rank, essentially, when the matrix loses rank, which has something to do with having information only along certain directions, right? So we no longer have all three unique pieces of information to find the roll, pitch, and yaw. We no longer have all November number of unique pieces of information to find all November states, right? That's the idea. So this is a similar concept that we're going to see coming up. So you can always test, if you're having problems, test to make sure that H is full rank. And I think there's just a MATLAB command, rank, to make absolutely sure that everything's going to be okay. Or it's, oftentimes you can kind of just convince yourself by thinking about it, whether or not this problem is going to work out. All right, so there's our aside on observability. Questions on that? Otherwise, most of the rest of the lecture is going to be one huge batch estimation example. All right, let's keep this train rolling then. So batch estimation example. All right. Suppose we set up a measurement, an experiment, I should say, to measure acceleration due to gravity. So that's what we're going to be doing. Suppose we set up an experiment to measure acceleration due to gravity. We will do this by dropping a ball and taking measurements with a Doppler radar, because that's the simplest way I could think of to measure acceleration due to gravity. Definitely not a stopwatch, but this is going to be useful because we're going to be handling Doppler measurements in the homework assignment. So bear with me. This is going to give us an opportunity to set up an estimation problem that involves Doppler measurements. So we'll say that the ball starts at some height, which we'll call h naught, and is subject to constant acceleration, which we'll just call A. All right. So we're assuming a uniform gravity field, which is fine for most practical purposes on the surface of the Earth. And some equations come to mind from high school physics, right? Velocity as a function of time is some initial velocity plus our acceleration times our delta t. And acceleration as a function of time, well, that's just A, that's constant. The height as a function of time, you know what, maybe I should change the order of these. Well, in for a penny, in for a pound, we'll just keep writing. Height would be h naught plus v naught t minus t0 plus this constant A times t minus t0 squared. So these equations should look familiar. Oh, I'm sorry. A over 2. There we go. It's 1/2 AT squared, essentially, right? So these equations from high school physics should look a little bit familiar. If not, they should hopefully make intuitive sense that this is going to be the governing physics of this problem, right? This is our mathematical model before we move forward. Now, let's talk just for a second about Doppler measurements, right? So Doppler sensors, like the sensors that police use to detect how fast somebody's going, right? Doppler sensors measure frequency shift. Frequency shift of reflected light. So we're going to say that our measurement looks like y is equal to f received minus f transmitted, which is equal to, we're just going to call that delta f, which is approximately equal to -2 times the transmission frequency divided by the speed of light times the velocity. That's going to be our measurement model, right? Before we move on, we have to clear up some things. What is C and what is f of t? So we will assume that the transmission frequency is known, and it should be a number that looks familiar. Transmission frequency is 35.5 gigahertz, which I believe I kept that number for homework too. And the speed of light is 3 times 10 to the 8 meters per second, which is fine for this problem. All right, so we've got our physics, we've got our measurement model, we've got our parameters. Time for the measurements. We collect the following measurements. Here comes the data table. So let's say we have time in seconds, and we have delta frequency in hertz. Okay. So at some 0.2 seconds, we measure 584.3 hertz delta F. At 0.5 seconds, I'm really trying to clear up my handwriting for y'all. So this is 1275 0.4 hertz. At 0.7 seconds, we have 1750.4 hertz. And at 1.0 seconds, we have 2431.5 hertz. So there's our data table. All right. So what are our states? So it's time to set up the next part of the problem. So what are we trying to estimate? Well, here's what I propose, and see if you disagree with me on this. We're after A, right? We're trying to measure A. I think it would be beneficial if we try to also measure V. So that's my, I'm going to put that forth as, I think V and A should be our states. And I think that you're going to see in the equations in a minute that it's going to work out pretty nicely if we try to measure V and A. I don't want to bother trying to measure H. For now, take my word for it, and then we're going to talk later about why that's a bad idea. But we're going to try to measure V and A. So what are our states? Sometimes the equations make it obvious what states you should choose, as I hope is the case in homework 2, problem 2. Other times you have to kind of pick something, start down that path, and then ultimately determine if you had it right or not. So what are our states? We're going to say that our states are velocity and acceleration. But specifically, what we're after is x at some initial time, which we're just going to write as x naught, which is v naught and a naught, right? Because we said that a is constant. So if we know a naught, we know a. That's really what we're after, is trying to find a. V is nice. Maybe we'll find some initial velocity too. Okay. So what is our measurement model? So let's take our measurement model and write it as a function, because we want y equals hx, right? That's our linear system that we know how to solve. Our measurement model is, so we know we want it to be y equals hx. We also know that we currently have this written as y is equal to negative 2f of t over c times v. So what I'm saying is that we can rewrite this as y of t is equal to, we're going to call this h. Let's see, because I don't want to call that h. Well, bear with me. We're not going to name this just yet, because I don't want to use the letter h until we're done setting up our batch estimation problem. So we're just going to write this out. It's going to be negative 2 transmission frequency over the speed of light, and then 0. So that's our 1/2 matrix, times velocity and acceleration. So our measurement is equal to this. This is not h, but this is a component of h. We're going to use this to build a larger matrix that we're going to call h. But this is how we set up our problem, right? Now we have a linear relationship between our state x. This is kind of h, but we're not quite there yet. And then this is our measurement y. Okay. So the problem is we're not after v and a, we're after v naught and a naught, right? So we need to use the state transition matrix to map all measurements to time. Oh, hang on, my pen is misbehaving. I should say to time t naught. Okay, so the way that this would look is something like this. Y at some tk is equal to hk phi tk t naught x naught. That's really what we're after. Okay. So we need this phi before we proceed, right? hk, I suppose this is hk. So we have part of our of our measurement sensitivity matrix, H. Really, it's phi that we need to focus on. So all we need to proceed is the state transition matrix. The state transition matrix. we will explore two methods to find it. Okay, so this is a good natural pausing point. So we've got our problem, we've got our physics, we've got our measurement model, we've got our parameters, we've got our measurements, we've determined our states, and we've set up a linear system to relate our measurement to our states. And now we know that because this is a batch estimation problem, because we're really after the initial velocity and the initial acceleration, but that's not what we're measuring. We're measuring velocity at different times, right? How in the world are we going to map back to that? Well, we need to use the state transition matrix. So apart from the fact that the state transition matrix might seem arcane and weird, and Paul, I don't know how to find that, don't worry, we're going to go over an example right now. But any other questions about this problem? Anything not make sense? All right, cool stuff. Let's keep this train rolling. So we're going to talk about one way of finding the state transition matrix, which is probably my less favorite of the two. But this is interesting enough. So state transition matrix. So this is an example within an example. Example one, we're going to call this method one. Okay. So we know that the state transition matrix has some properties that are useful to us. The first is that the state transition matrix, the derivative is equal to f phi, where that's the same x as x dot is equal to fx, right? It's the same f. So the f that maps between the state and the derivative of the state is the same matrix that maps between the state transition matrix and the derivative of the state transition matrix. So that's an interesting bit of information that we're going to use in a moment here. We also know that phi naught, which is to say phi mapping between initial time and initial time, well, that needs to be the identity matrix, right? If we're trying to map the state from some time to the same time, then we need to leave it alone. And the identity matrix is the matrix that leaves things alone, right? It's the equivalent of the number one in matrix land. Okay, so what do we know about our dynamics? So let's explore this for a minute here. V dot A dot is equal to what? Well, the derivative of velocity here is acceleration, right? So this would be written like so. Derivative of velocity is acceleration. Derivative of the acceleration, well, we're saying that it's zero. We're assuming a constant acceleration system. So this is now our F matrix. Okay. So we can combine this information and the information that phi starts off as the identity matrix, and we can actually go through and set up some differential equations that allow us to solve for the individual terms of the state transition matrix. So we will divide phi into 4 quadrants. It's going to get a lot easier in a second here. So I'm going to call this phi is equal to phi11, phi12, phi21, phi22. Okay. And so we know that phi dot is equal to f phi. So let's just think about how that would work out, right? So it's essentially this F matrix times this phi matrix. And so hopefully it's clear that this is going to give us phi 21, phi 22, 0, and 0. So there's our phi dot. All I did was I multiplied the F matrix by this matrix. Hopefully it's straightforward where that all comes from. So that actually sets up a relatively simple set of differential equations that we can solve pretty much just in our heads, essentially. So this gives us four differential equations with four initial conditions. Okay, so trying to make as much room as I can here. So let's talk about phi 1, 1. So phi 1, 1 initially is equal to 1, right? Because we know that phi starts off as the identity matrix. So it starts off as 1, 0, 0, 1. So phi 1, 1 starts off as 1. And we also know that phi 1, 1 dot is equal to phi 2, 1. Okay. Not super interesting on its own. Let's look at the whole problem. We're going to come back to this. Okay. Phi 1, 2 initially is 0, right? Because it starts off as the identity matrix. Phi 1, 2 dot is equal to phi 2, 2. Okay. Again, not super sure what that means. Let's keep writing equations. This is going to come together. Phi 2, 1 initially is also 0. And phi 2, 1 dot is equal to 0. And phi 2, 2 initially is equal to 1. Phi 2, 2 dot is equal to 0 as well. Okay, so do these initial conditions and differential equations all make sense? If anything is like a record scratch, what the heck is Paul talking about? Let's discuss it right now, because otherwise I'm going to ask people to solve these, and we'll start with the easy ones, and then we'll get a little bit spicier and spicier. Okay. So I'll take a volunteer, whoever thinks that this is starting to click and make sense. Let's start from the bottom and work our way up. So if this is the case, let's just look at phi 2, 2, right? The bottom right element of phi. It starts off as 1, and then its derivative is 0. So what does that tell us about phi 2, 2? If it starts off at 1, we got something?
It should still be 1.
Yeah, it's going to be 1 forever. There we go. All right, and let's keep this party rolling. So then we have phi 2, 1, which starts off at 0, and then its derivative is 0. So what is phi 2, 1?
It'll be 0 forever.
Also 0 forever. Well, I should say it's 0 also forever. Very good. Let's skip one. Let's go up here. Phi 1, 1. So it starts off at 1, and then its derivative is phi 2, 1. But we just said that phi 2, 1 is 0, and it's never going to stop being 0. So that means that phi 1, 1 is something forever. Oh, y'all are either asleep or you're feeling really shy. That's all right. This is 1 forever. Hopefully that makes sense. This one's going to be a little bit trickier. Phi 1, 2 changes. Right? It starts off as 0, and then its derivative is phi 2, 2, and its phi 2, 2 is 1 forever, which means its derivative is 1. Okay, so what we're going to find is that phi 2, 2, or sorry, phi 1, 2, initially is essentially, you could think of it as t naught minus t naught, which is 0. And so what it is moving forward is essentially t minus t naught, or delta t. So its derivative is 1. So essentially it's going to be just a straight line. And you can think of it as the time since we started taking measurements. This is essentially what phi 1, 2 is. So what that means is if we put this all together, is that phi mapping between the current time and the initial time is 1 t minus t initial 0, 1. Right. That is our state transition matrix that we need to proceed in this problem. All right. Now, all of this was one way of finding the state transition matrix. I want to show you another way, which I actually like even better and is fewer steps mathematically, but sometimes it's nice to see multiple methods, you know, all roads lead to Rome, that sort of thing. So let's try another method of finding the state transition matrix. And assuming that we don't make any mistakes, we should get the exact same solution because math is math, right? So state transition matrix, method 2. I like this one better because it uses matrix vector calculus. And let's see, did I underline the last one? Okay, yeah, I want to be consistent. There we go. Nice. Okay, cool. So here's really what's going on with the state transition matrix, right? Phi mapping between the time and the initial time is really the derivative of the state with respect to the initial state, right? You can think of it as a Jacobian, which tells us the sensitivity of some vector to some other vector. And we find that by taking the derivative of a vector with respect to a vector. Now, we're saying that in our problem, x of t is velocity and acceleration, which per our mathematical model is v naught plus a naught t minus t initial, and then a is just a naught, right? And then we know that x naught is v naught and a naught. So here we go, time to take some derivatives. Actually, in this problem, because it's a scalar problem, it's just going to be regular calculus instead of matrix vector calculus. But you could see how this would scale up to matrix vector calculus. So the derivative of the state with respect to the initial state, well, that is what? It's going to be the derivative of velocity with respect to initial velocity, the derivative of velocity with respect to initial acceleration, the derivative of acceleration with respect to initial velocity, and the derivative of acceleration with respect to initial acceleration. Reminds me of those Punnett squares from biology, right? Gregor Mendel working on P's. So what is the derivative of the velocity with respect to the initial velocity? Well, the velocity is v naught plus a naught t minus t naught. So what's the derivative of all that with respect to velocity? I'll take any guesses if someone's feeling brave. So if v is v naught, we got any takers on this one, or is everyone feeling shy today?
Is it just 1?
It's just 1. Very good. It's essentially the derivative of, yeah, v with respect to v naught. The whole second term would go to 0. And then the first term, derivative of v naught with respect to v naught, is just 1. Very good. What about the derivative of, let's skip the top right for now. We're coming back to it. Derivative of acceleration with respect to v naught. Well, acceleration has nothing to do with v naught, so 0. Okay. And then derivative of acceleration with respect to initial acceleration, well, that's all that it is. So that's going to be 1. Okay. The derivative of velocity with respect to initial acceleration, well, let's look at this term by term, right? The derivative of v naught with respect to a naught is 0. The derivative of a naught t minus delta t with respect to a naught is t minus t naught, not t minus delta t. So this term gives us t minus t naught. So this second method uses a little bit of calculus. It requires that we have a nice mathematical model for our problem that we can take derivatives of. So you can't always use method 2. You can't always use method 1. But in this case, because this problem is so simple, we can use both. And we see that we get the exact same state transition matrix, which it would be a bummer if we didn't. That would kind of imply that we had gone loco somewhere along the line. So like, hey, look at that. Okay, so now we still haven't solved our problem, right? All we've done is the setup for our problem. we still need to take this state transition matrix and incorporate it into the original Doppler batch estimation problem. So let's do that now. So returning to our batch estimation example, so H sub k times phi mapping from T naught to Tk is equal to what? Well, remember that it's not exactly our measurement sensitivity matrix, but it's kind of our HK, so to speak. Maybe I'll put a little dotted line right here to make it clear. HK is -2 transmission frequency over the speed of light, and then 0, because we're not directly estimating A. Okay, so that is -2 transmission frequency over the speed of light, and then 0. And then this multiplies by 1, T minus T naught, 0, and 1. Okay, so this multiplies to be what? Multiplies to be -2 transmission frequency over the speed of light, -2 transmission frequency over the speed of light, times whatever the time is when measurement K comes in, minus T0, and this is a matrix, right? So what that means is we can stack this to produce our linear measurement model. So in our case, I'm going to simplify things a little bit. T naught is just 0. And so that allows us to write a system that looks like this. Y1, Y2, Y3, Y4 is equal to, I'm going to take the -2 transmission frequency over C and just factor it out. And our H matrix, that looks a little bit sloppy. I'm going to try harder. Our H matrix is going to look like 1 and T1, 1 and T2, 1 and T3, 1 and T4. And then finally, we have initial velocity and initial acceleration. So this whole thing here, which includes the -2 transmission frequency over the speed of light, this is H, this is Y, and this is X naught. So we have something that looks like Y is equal to H X naught. We're still not quite done. We have our problem. It's set up. We're ready to start solving it using least squares. But I'd like to solve this using maximum likelihood estimation, which means we need the measurement covariance matrix R. So we're going to keep on moving. We still need the measurement covariance matrix R to proceed. I'm going to assume, so this was not something we gave yet, so this actually really should be in the given of the problem. If we assume the Doppler measurements are corrupted with noise having 0 mean and sigma delta F is equal to 5 hertz. So our 1 sigma error for each measurement is 5 hertz. So we're treating it as our original measurement, our measurement is the truth plus a random number, which is distributed as a Gaussian, having 0 mean and a standard deviation of 5 hertz. And I'm going to try a little bit harder at drawing a decent delta because I kind of phoned it in there. That's a bit better. So then we can say that R is equal to sigma delta F squared I 4/4. So in this situation, right, there's essentially two situations that you could find yourself in with the measurement covariance matrix. As we've set it up, because this problem is very simple, it's essentially just one number scaling the entire, like what is otherwise an identity matrix, essentially. And so that means we have the same uncertainty for each measurement. So it's not going to bias our choice of measurements in thinking that one is more trustworthy than another. Essentially, it's going to push through the same state estimate that least squares would. But now this tempers our expectation when the time comes to find the covariance matrix. So R is absolutely critical in finding the covariance matrix. As defined, it's not going to make our MLE problem all that much different. But it's going to make our covariance computation quite a bit different. So finally, we can compute our state and our covariance. And so we're saying that X naught star is H transpose R inverse H transpose R inverse Y. And P is equal to H transpose R inverse H inverse. Okay. If we do this, if we actually set this up, and you're going to set something up very similar to this on the homework, but for now, if we set up something like this, then what we'll get, I'll spare you the suspense. X naught star is equal to negative 0.518 meters per second and negative 9.773 meters per second squared. Okay. Now we know that the true solution, I'll just give that to you, which was used to generate these measurements, is, so this is the true X naught, is negative 0.5 meters per second and negative 9.81 meters per second. Okay. So that's pretty close. We made it pretty close. We can also say that our covariance is P is equal to, okay, here comes some numbers, 5.8 times 10 to the negative 4, negative 7.8 times 10 to the negative 4, negative 7.8 times 10 to the negative 4, and 1.3 times 10 to the negative 3. And so from here, if we take the square root of the top left element and the square root of the bottom right element, that tells us that our uncertainty regarding our initial velocity is 0.024 meters per second, and our uncertainty regarding our initial acceleration is 0.036 meters per second squared. So what that means is our estimate of our velocity, if you look at the difference between our estimate and the true velocity, it's about 0.018 meters per second, which is within one standard deviation of the truth. And then our residual when it comes to the acceleration is whatever 9.81 minus 9.773 is, which is less than 0.036. And so what happens? Actually, I think it's very similar to 0.036. Might even be equal to 0.036. So what this tells us is that our standard deviation, or sorry, our state was about one standard deviation away from the truth, which is reasonable given the nature of our estimate, right? And so, yeah, that's it. Victory achieved. We're going to say that X is around, sorry, X naught star, our estimated thing, is around one standard deviation from the truth. which is reasonable given the amount of noise that we have on these measurements. And that's it. So we've walked all the way through, and we have kind of an epitaph on this, and then we'll take a little break, but just scrolling up for a minute. We've set up the problem of taking Doppler measurements of a ball that's been dropped from a height. We have our physics that describe the situation. We have our measurement model from the Doppler equations. We have our parameters. We have our measurements. We've set up our state, and that gives us the ability to compute this kind of linear system, y is equal to hk times the state. The problem is that the state is always changing, so we need the measurement sensitivity matrix to map the initial state onto measurements that come at different times. You'll notice that all of these measurements happen later than the initial state. So we're kind of going back in time, trying to probe the state of the system in the past, given measurements in the future. And so that requires us to compute the state transition matrix. We went through a differential equation method of finding it, and then a calculus method of finding it. We get the same both times. When we return, we can set up our measurement sensitivity matrix H. We have a linear system of equations that allows us to solve using maximum likelihood estimation. Finally, we kind of shoehorned in this discussion of the measurement covariance matrix R. When we compute our state, it's wrong, but it's close, and that's typically how estimation theory works. And we can actually quantify how far off it was because we have our covariance P. And all of these are things that you will be asked to do on homework 2, problem 1. So essentially, I'd like you to base it off of this. And we're going to pause in a minute to take a break. But first, I want to just cover one last bit of advice, and then we will pause for a moment here. So first, note, what if we instead wanted to measure, or sorry, not to measure, but to estimate. So what if we were too greedy? We weren't happy with initial velocity and initial acceleration. We also wanted initial height. So what if we picked a different state? So x naught is equal to h naught v naught a naught transpose, so it's a vector. If that were the case, if we work this out, we would find that hk is equal to -2 transmission frequency over c times 0, 1, and t minus t naught. And this is a problem because if we were to stack several of these, we would find that the columns of h are not linearly independent. This would become an unsolvable problem, right? This would mean that this is unobservable. Now, we could also arrive at the conclusion that it's unobservable if we just think about it for a minute, right? If you have a radar gun that's measuring the speed of the ball as it drops, that tells us absolutely nothing about how high off the ground the ball is. Now, to be fair, it also tells us absolutely nothing about the acceleration, but the batch of velocity measurements over time allows us to compute the acceleration. We say, okay, well, I don't know the acceleration. I never even measure the acceleration, but I'm measuring velocity at different times, and that gives me enough information. If you think about it, you know your velocity at one time, you know it at a different time, finite difference. You can put together an estimate of your acceleration, even if you never measure it directly. But there's no way to measure height, because if you think about it, a ball dropped from 10 meters would have the same velocity profile as a ball dropped from 100 meters or a kilometer, right? So height does not factor into the physics describing velocity and acceleration. That makes it unobservable. So you could kind of just convince yourself with logic, or if you wanted to be more rigorous and quantitative about it, you can actually put together H and find that the columns of H are not linearly independent. They are linearly dependent, meaning that this will be an uninvertible problem or an unobservable problem, essentially. So my advice would be, here's the punchline. If your system is unobservable, you have got two choices. You can try to estimate fewer states, but just throw some overboard. Or buy more sensors because you're not measuring enough. So you have not enough information and you're trying to estimate too many things. So you can either estimate fewer things or come back with more information. Those are your choices. All right. So that was, we've been going for an hour now. So why don't we take a break? But this was a lot. Does anybody have any questions on this batch estimation example? Otherwise, why don't we say, take a break, come back at 7:10, and then we'll keep going. But I'm going to stick around for the whole break in case anybody has any questions.
Paul,
Yeah,
I have a quick question. You might be
sure.
intending to cover it next.
Mhm.
So say if we didn't know the uncertainty in our sensor, but we knew the true values,
Mm-hmm.
how would we then just use the difference between our estimate and the true value to get our covariance?
So I wouldn't do it that way because what that is your residual or your error.
Right.
So is this in the case of homework 2, problem 1, having
Yes.
difficulty finding P?
Or I think I found it, but I'm not certain I found it the right way.
Oh, I mean it's this, right? It's H transpose R inverse H inverse right here.
But I don't think you gave us sigma, unless I've.
Didn't I? Let's go read it.
I don't think you did.
Um, oh, did I screw up? Hang on, let me check my notes. That would be a blunder on my part if it's not in there. Let's see, 1 sec, homework 2. What do I have in my notes? Hmm. Oh, that's problem 2. Hmm. Did I say? Oh, here it is. Gaussian clock noise with a standard deviation of 1 nanosecond. That's it.
Okay, missed that. Sorry.
No, I missed it too because I just read through it in front of you and didn't see it. So it's I think I specifically didn't put it as a number because I wanted it to be easy to miss. And it's occurring to me that whenever I'm cheeky and make something difficult, it like ruins someone's day. So I might back off on that a little bit. But yeah, so it's supposed to be 1e to the -9 is your sigma. Good question. Uh, I'm just trying to fix my typo up at the beginning of this lecture. I had a brain fart. I don't know how noticeable it was, where I couldn't remember where the apostrophe goes in the word your. So I just tried it 2 different ways. It's like I want to go back and fix that. Y-O-U apostrophe R-E. Yeah. Reminds me of the bit from How I Met Your Mother where Ted is a professor and he can't remember how to spell the word professor. So he's just kind of like guessing in front of the class. It's like that's, yeah, art imitates life. All right, let's keep this train rolling. Welcome back from break. Hope everybody's feeling refreshed. So I hope that this problem kind of sets us up for success on homework 2, problem 1. I only have one more page of notes to go through, so it's going to take about maybe 10, a little bit over 10 minutes to do that, and then we are gonzo. So this next bit is just assistance on homework 2, problem 2. And then after this, y'all are dismissed after this. So let's see. Common question that I get. Common question. I had a number of people come to me with this. What is H? Right, we've seen the letter H thrown around a lot in the past 3 lectures, but what does it mean, right? And so my answer, which might not be super satisfying, is you decide. Right? So H, by definition, is the measurement sensitivity matrix. And it relates our state to our measurements. But really what happens is we're going to need to sit down and do some math and find H. H is usually not given to us, something we need to find. But we're ultimately after a system that looks like y equals hx. That's what we're trying to find, right? So we assume for this problem, for both problems on the homework, a linear measurement model. Which looks like y is equal to hx plus nu, where we have some information about the noise and we have some information about the measurements, and we're trying to find the state x. Now, on homework 3, we're going to throw that right out the window and start doing some nonlinear estimation, so have fun with that. But for homework 2, it's going to stay linear for now. So let's see an example, and we're basically just going to use the example from the homework. So here's an example. Draw a little picture. So let's say we've got our world frame here with X and Y and Z. And let's say that we've got a very well drawn Orion spacecraft with little solar array wings. And it's got some position R and it's got some velocity V. And let's say that we've got a beacon on the surface of the moon, it's flying overhead, where we're going to call this pi, and this vector is r minus pi. Right? So what we're saying is I'm trying to remember, is the spacecraft transmitting and the beacon's receiving, or the beacon's transmitting and the spacecraft receiving? Because that kind of matters. Oh, hey, look, it looks familiar. The spacecraft sends out a signal with a known transmission frequency. We want to estimate the velocity of the spacecraft in the local beacon frame. So the beacons are doing the receiving. Okay, fine. So the component, hopefully this is obvious, but if not, let's go through it. The component of the velocity in the ith beacon's line of sight is what? Well, it's going to be velocity transposed onto some vector r minus pi normalized, which is the same thing as v transpose r minus pi divided by the norm of r minus pi, right? So we're saying it's this vector right here. So I'm going to make it red here. That's what that is. But it's the line of sight direction, so the magnitude doesn't matter, right? So we're just saying, okay, this direction, velocity transpose onto that direction, is going to be not exactly what we measure, but it's going to be what we're pointing at with our measurement. Now, we can also say that we have some unknown range where rho I is equal to r minus pi, right? So that's the unknown range, the distance from the ith beacon to the spacecraft. So we've got the distance and we've got a component of the velocity. So our measurement model looks like this. And I believe I just gave this to you in the homework problem, but the ith Doppler measurement is delta fi is equal to -2 transmission frequency over c velocity transpose r minus pi divided by the norm of r minus pi. So all it is the velocity component times -2 transmission frequency over c. So nothing too arcane. Might look a little weird when you see it for the first time. Yep, I just throw it at you there. Might look a little weird when you see it for the first time, but hopefully in the context of today's lecture, this seems very natural. Okay. Now, we also know one other thing. We also know that delta ti, essentially the time of flight between when the signal was sent and the signal received, well, that's just the range divided by the speed of light. Now, this is a very simplified measurement model. We're going to get into fancier forms of Doppler and time of flight based radiometric navigation in the next couple of classes. We're doing a very simple version of it in this problem, right? But so the time of flight is equal to the range divided by the speed of light. Okay. We also know that the weirdo professor is giving us this weird measurement, which we're calling mi with a squiggle because we know that there's noise on there. And that's equal to delta fi delta ti plus some noise epsilon I. So we're using epsilon instead of nu in this case, but it's the same thing, right? Now, we should make a point that this measurement mi was chosen to keep the problem linear. Maybe at the end of the semester, I'll do like a behind the scenes where I show you how I cooked up all these homework assignments, because a lot of the lectures in this class I borrow either from Dr. Anderson's spaceflight mechanics or Dr. Christian's space navigation course. Towards the end, it's going to be lectures that I make up from scratch, and you know, I obviously put my own spin on it. But these homeworks are almost completely made up by me, so we're not borrowing stuff from other, you know. So that showing the, I think I went through 10 pages of math trying to find a linear problem that was of a reasonable difficulty that we could try to solve for homework 2, problem 2. And ultimately, the way that I kept this problem linear was by giving you this weird measurement, which if you try to wrap your head around, you're just going to be walking down the path of insanity because it doesn't mean anything. Delta F times delta T, like why would we measure? We would measure those independently, right? Ordinarily, you would measure those separately. In this problem, you're given those multiplied together because it keeps the problem linear. So bear with me here. Based on what we just said, isn't it true then that delta Fi times delta Ti, well, that's going to be what? It's going to be -2 transmission frequency divided by the speed of light times velocity transpose r minus pi over rho I, and then we're multiplying this by rho I over c. So cancel, c squared. This is equal to -2 transmission frequency over c squared, velocity transpose r minus pi. Okay, so now all of this is mi. Okay? So that without noise, we're not taking noise into account just yet. Okay. So then if I say we're going to define yi, and that's defined as mi times c squared over -2 transmission frequency. All we're doing is moving some weird stuff. We're just getting all the stuff into the left-hand side of this equation, and we're going to call that the measurement. well, then this is equal to V transpose R minus PI. Okay? Or you could write this as V transpose R minus V transpose PI, or you could also write this as V transpose R minus PI transpose V. Totally fine to write it that way. Okay, really there's going to be some noise on there, right? So yi with some noise is essentially just the measurement that you were given by me times c squared over -2 transmission frequency. And we can now set up a linear system of equations that looks like this. Yi with some noise is equal to 1 negative pi transpose V transpose R and V. So this is going to be part of your measurement sensitivity matrix. You would need to stack several of these, but this right here is the state. So you've got the three components of your velocity, so it's going to be a 4x1, right? You've got the three components of your velocity. You also have V transpose R, which is kind of a stowaway. Like I don't really want that to be there, but there's no easy way to work out the equations to solve for V on its own. So we're just going to say, to heck with it, you know, get on the boat. We're all going. Come on, let's move. And we set up an equation that looks like this. We accept that because we are kind of weaseling out of trying to find V specifically, we need to take an additional measurement on. So we need at least 4 measurements to solve this. But I believe we're given 5 measurements in the problem. Yep, there's 5 beacons. And so this in no way finishes homework 2, problem 2, but I think that this is the hardest part, is trying to get from the equations that I gave you to a linear system that looks like y equals hx. Because from this point forward, it's all pretty much plug and play. Like there isn't too much in the way of head scratching that I can think of. But yeah, that's it. That's hopefully demystifies homework 2, problem 2. I might have helped a little bit too much. Those of you that haven't even started the homework yet, this probably helps too much because, like, you know, you're meant to scratch your head on it for a little bit. But I think a good chunk of you were already batting your head against the wall, and like you deserve a bit of a break. If it's not obvious, then absolutely let's make it make sense. But yeah, that's it for me. So if you have any questions, I will stick around. I'll probably record the questions and answers as long as you don't mind, because I know that not the whole class could be here today. So anybody that has any questions for me, I'll record that too, just for everybody else's education. But yeah, other than that, class is dismissed. Thank you all for being here on your day off. Hope you enjoy having tomorrow evening off. Hope that you make your mental health a priority and you take a break at some point in the next day or two. But yeah, thanks for coming, everybody.
I have a question.
Yeah, I haven't answered.
Oh, can you go back to the page that you were
Sure.
sharing?
Yeah, let's go right back to it. There we go.
So since we were given 5 measurements from the 5 beacons, but the state is going to be a 4x1, should we just use the measurements from only 4 out of 5 of the beacons?
Well, why not use all 5?
Would the Oh wait, I guess it's fine then.
Yeah, it's
I
totally
thought
fine.
like I don't know. I didn't think the matrix math would work out, but now I see it does.
Yeah. So what you'll see is that H is a long matrix. We typically have more measurements than there are states. And actually, that was a assumption that went all the way back to here, right? So if H is an m by n matrix, we're assuming that it's a tall matrix. There's more equations than unknowns. Because it is not a square matrix, it's not directly invertible, but we can use the pseudo inverse, which is H transpose H inverse H transpose. But I believe for homework 2, problem 2, we use least squares, and then we also use MLE later on, which is right here. So we're going to want to use both of those equations. So we still need to sort out the matrix R, but I think that that is pretty straightforward as written in homework 2, problem 2.
Okay.
right, keep the questions coming. Anybody else?
I was doing question 2, and I got answers for both, like the least squares and the ML and the MLE. And I know the last question asks like, oh, are there any big differences? But I got like a really huge difference in the K value, and I like don't know what to make of it. Like the X and the Y
Oh,
values are like pretty close, and then the
yep,
Z value is different.
yep, I do. I remember that now. So I remember the way that it was set up is that K is like a grossly incorrect number if you don't. I believe it's. I'm trying to remember which was which.
Like
Isn't it
I got
huge?
like a negative number for least squares and then a positive number for MLE.
And isn't one of them very, very big and the other one's actually pretty tame?
One like the one for least squared is like about the same magnitude as the X and Y, but the
Hmm.
one for MLE is like just not.
Okay.
It's
Yeah,
like
I'm trying to
maybe
remember
it's like
what.
maybe like a fifth of what the X and Y are.
Okay. Yeah, I'm gonna go back through and find my, because I don't have the numbers in front of me to answer that. But let me kind of guide your thinking, and we can talk about this also on in office hours if you can make it. I can give you a better answer then. Right now, I'm just kind of focusing on getting folks to the point where the mathematical model works. But if you think about the geometry of the problem, right? What you're essentially doing is you have some beacons that are all grouped pretty tightly together on the moon, right? So they're a series of observers, and they're all measuring the spacecraft velocity. But the spacecraft is pretty far overhead, and its velocity is mostly perpendicular to all of the beacons, right? And so what that means is we're going to have great information, a great certainty about the spacecraft in the direction that we're measuring, but in the direction that is perpendicular to the direction that we're measuring, it's going to be poor. Actually, I think I have that backwards. Z is the one that's going to give us the greatest uncertainty as it's set up, essentially, because we have great information about the velocity in the other two components and not so great information in the Z direction. So it has to do with observability. And actually, if you look at your H matrix and you look at your, how close to singular it is, we'll see that it does not give great observability along the different directions. And you can even do like a singular value decomposition on H, and that will give you an idea of the relative observability along the different directions. And I believe the observability is poor along Z, but I'm going to go back and get some actual numbers so that I can have a more informed discussion with you if you can make it to office hours on Wednesday.
When are the office hours Wednesday again?
Same as class time. So 5 to 7 for me, 6 to 8 for you.
Okay.
Yep.
All right. Thanks.
Cool. And I'm going to make a note to myself to get on top of that, get some numbers ready.
Yeah, because I was wondering when I like had R is just like a straight what is it? Straight identity matrix. Like the numbers were like I got the exact same numbers, but as soon
Hmm.
as I changed it, it like got something rare, like really different.
Yeah, I believe because I put different amount when I was making up the problem, I put different amounts of noise on the different beacons. And so yeah, you can see here that beacon 4 is very trustworthy compared to the others because it has the least noise. And then beacon 2 is the least trustworthy because it has the most noise. And so yeah, if you're building your measurement covariance matrix, then yeah, you're going to be differentially trusting certain signals over others.
Hey, Paul.
Yeah, what can I do for you, Calvin?
Yeah, can you actually go over the state transition matrix, how you did it for method one again? Over.
Sure. Yeah, absolutely. So we'll do just a quick review of method 1.
Yeah,
Uh,
I thought I understood, but I'm looking back at it, I don't know, I'm getting confused on myself.
okay. Yeah, absolutely. So does that mean that method 2 made more sense to you?
Yeah.
Okay. So yeah, so method 2 is essentially just taking the derivative of the state with respect to the initial state. And so
Mhm.
that's pretty straightforward. Although, you need to actually have equations that you can take derivatives of. And if these were vector equations, we would start getting into matrix vector calculus. For the case
Mhm.
of the first method, we're leveraging two bits of information. The first is that phi follows the same differential equation as the state x. So x dot is equal to fx, or maybe you might have seen like ax in like ModCon or something like that, just a different letter. Then phi dot is equal to f phi, right? So the same dynamics that describe how x changes over time describe how phi changes over time. And similarly, we know that phi has to start out as the identity matrix. So at the initial time, phi is identity because you're just mapping from some time to the same time, right? So of course that's going to be the identity. Do those two bits of information make sense? Just kind of a checkpoint. So far,
Yes.
okay. So that gives us two bits of information. We know that phi naught is the identity matrix, which means we know that phi 1 starts as 1, phi 1 2 starts as 0, phi 2 1 starts as 0, and phi 2 2 starts as 1. All right, so far so good.
Oh, okay. Yeah.
Oh, was that it? Was that the weird bit?
I think so because I was kind of that because of the initial conditions of like 1001. I was like how do you pull out the numbers on it? But that makes
Okay, was that the missing piece? Did the rest of it make sense?
Um.
Or keep moving?
Can you keep moving for now? Yeah.
Yeah, let's keep moving, make sure it all makes sense. Okay, so then the next bit I'm saying is that phi dot is f times phi. Well, what is f? F is the matrix that describes the relationship between the state and the derivative of the state. And we can get this pretty much just by thinking about it. Now, if this were a different problem and the physics were a little bit more complicated, it would take a little bit more thinking about it. But hopefully it makes sense that these are the dynamics governing our system, right? So v dot, the derivative of velocity, is just acceleration. So this top row is 0, 1. And then a dot is 0, 0, because a dot is nothing, right? So we're assuming constant acceleration. Right? If acceleration were a function of position, like in the two-body problem, then we'd have to rethink this, and this would be nonlinear. It'd be a bit of a pain. But for now, f looks like this. Okay, great. So then that means that phi dot is equal to f phi, and I'm defining phi as being phi 1 1, phi 1 2, phi 2 1, phi 2 2. So if we multiply f by phi 1 1, phi 1 2, phi 2 1, phi 2 2, we're going to get this, which is phi 2 1, phi 2 2, 0 0. So that means that phi 1 1 dot is phi 2 1, phi 1 2 dot is phi 2 2, phi 2 1 dot is 0, phi 2 2 dot is 0. So I take all the initial conditions and all of the differential equations and then just stack them like this, just so we can kind of think about them one at a time. If phi 1 1 is initially 1 and its derivative is phi 2 1, and so you kind of have to read this out of order. Phi 2 1 is 0. And if phi 2 1 is 0, then phi 1 1 dot is 0, which means that it starts as the number 1 and it never stops being the number 1 because it has no derivative.
Okay.
And then we can play the same game for phi 2 1 and phi 2 2. So those are both going to be their initial state forever. The only one that changes is phi 1 2. And this one takes a little bit more thinking. But essentially, phi 1 2 starts as 0, and then its derivative is 1. And the equation that best describes that is essentially just saying that it is time itself, like delta t. Starts off at 0, and then every 1 second it's equal to 1 second, and then 2 seconds it's equal to 2 seconds, right? That sort of thing. So it's linear in time. Yeah. Does that all gel a little bit better this time around?
Yeah, for sure. Yeah.
Okay.
Thanks.
Excellent. Sure,
Okay.
absolutely.
All right. Thank you so much.
Yeah. Now, if anybody has any hyper-specific questions about homework 2, then I'll stop the recording and we can go on and talk about that. But for now, I wanted to include as much of our discussion as possible for people that couldn't be here, or for y'all if you wanted to go back and revisit this tomorrow or some other future time. But any other general questions that would benefit everybody? Otherwise, I'll stop the recording.
Oh, I guess I have one more question.
Sure. Yeah, keep them coming.
Yeah, maybe a little bit related to homework, but when I was doing it, I thought the state variable could or like the x variable, like the state variable has to be like some kind of exact, like I don't know, like kind of like a exact relationship, like velocity or position. But from what I've seen is like it could be like anything basically, as
Yeah,
long as
exactly. The state
Oh.
is what you're trying to, so that's the thing. And I think maybe I might have misled you in the first lecture when I said that we're all about estimating position, velocity, and attitude. We very frequently find ourselves, because the math works out that way, having to estimate things that we don't care about in addition to the things that we do care about. So we're going to go through in the next lecture kind of a convoluted way of finding the position of a spacecraft given essentially radar measurements that we take from ground stations, talking about radiometric navigation. And what you'll see is that there's no way to do that without also measuring and estimating the clock bias of the, because you've got the time of flight, so you need an incredibly sensitive clock to measure that. And that clock is going to have a tiny bit of bias on that. And if you don't estimate the clock bias, the whole problem just doesn't work mathematically. And so we will often throw things into the state vector that we don't necessarily care about because we can't travel without them, so to speak. Like they're going to stow away on our ship, and that's fine because the ship's still going to make it to port. But in this case, we have velocity and v transpose r, and that's okay because later we're going to get v, and I really don't care about v transpose r. We can compute it. Actually, that's just more information if you think about it, kind of. It gives us a little bit of information about our position, but really we're after v. And so it's okay to have more things if the math decrees it. You want to kind of follow what the math is saying versus planting your staff in the ground and saying, no, 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 this is it. I declare that this will be the state, and I'm not open to any changes, because that's a great way to kind of shoot yourself in the foot when you're trying to set up an estimation problem. So,
Okay.
perhaps. Yeah,
That
absolutely.
makes perfect sense. Yeah, I don't. I yesterday I just spent the whole entire my afternoon trying to find some way to like make it into like one variable for some reason.
Oh, I'm sorry. I hate to think I blew your whole afternoon on you, Calvin.
No, that's fine.
All right, well, do
But
me a favor and take the rest of the night off, or I don't know, you're in charge of your own time management, but please be good to yourself and take a break at some point.
yeah, because I thought like it has to be like it has to be like some sort of like velocity, as I said,
Yeah.
velocity position. So I was thinking like I have to like convert
Hmm.
for some reason like
It does have to include V, but yeah, we can have other
yeah
stuff too.
for some reason I need to convert like velocity and some sort of like related to like angular momentum or something like that in order to put it into the state variable. But now I understand it. It could just be all the unknown variables we finding basically.
Yeah. Any unknowns that seem appropriate to find, you can put them in the state essentially. Um, Now you do run the risk of being overloaded. You can't just make the state arbitrarily large because we need enough measurements and the problem needs to be observable and so on and so forth. But within reason, yeah, you can throw extra things in the state and get away with it. Yeah,
Okay. Thanks so much, Paul.
absolutely. Any other generic questions? Otherwise, we'll switch to like a specific questions mode. Just want-
Yeah.
Yeah, keep
So
it coming, Justin.
why is it that when you solve for the state vector in this problem, the
Mhm.
V transpose R term is a scalar rather than a vector?
Well, let me answer your question with a question. Is V transpose R a scalar or is V transpose R a vector?
Well, I guess it is a scalar, but I don't really understand why.
Isn't it? Oh, sorry, I dropped my pen. In general, right? If you've got some vector A, which is a 3 by 1, and you've got some vector B, which is a 3 by 1, then A transpose B, which is the same as A dot B, that's going to be a scalar, right? It's going to be A times B times cosine of the angle between them.
Okay, yeah.
Yeah,
Okay,
I
got
think
it.
you're just overthinking it,
Yeah.
or yeah, I think it's just a misconception. But yeah, so V transpose R is going to be a scalar, which is like neat. It doesn't really give us what, like, I can't do anything with that. I don't care. Like I'm here for V. V transpose R is kind of neat, I guess. I mean, in theory, it gives us one component of our position. V transpose R is actually what we call radial velocity, or sometimes you'll see that written as range rate, right? It's the amount of your velocity. Actually, I take that back. V transpose R, where R is normalized, would be range rate. So this is giving us something weird. It's like the component of our velocity along position or the component of our position along velocity. So it's kind of useful information, I guess. But yeah, it's just there as a stowaway, essentially.
Okay. So one other thing then.
Yeah.
In this derivation, we just kind of neglected the uncertainty term.
Mhm.
Wouldn't we have to scale the uncertainty somehow, just like we scaled our measurement M to turn it into Y?
Let's see. So we have the uncertainty on. Oh, I see what you're saying. Yeah, because M is delta F delta T plus epsilon, but then Y is MI scaled by the speed of light squared over -2 transmission frequency. Yeah, now that I think about it, did I do that? How did I do that? Because I give you the M's and the sigmas. Hmm. You know what? That's a good question, Justin. I don't have an answer for you right now. Would you do me the honors of asking that same question again in office hours? And I'll be able to give you a more satisfying answer. Because I think either A, you don't need to worry about it, or B, you definitely do need to worry about it. But at the moment, my brain is failing me. So
So
Wanna
what I
talk
did to test this was I just took my R matrix and I multiplied it by the C squared over -2FT term.
Mhm.
And it ended up not really affecting the answer. So I think it doesn't really make a difference unless I did that wrong.
Does it affect the covariance?
I didn't check that.
Okay. Because so what would end up happening is if you take R, the relative values within R give us the relative amounts that we trust the different beacons. So scaling the whole thing would not change the relative amounts that you trust each of them, but scaling the whole thing would change your uncertainty of the entire problem. So we would still need to kind of go back and revisit that about the uncertainty of the entire problem at large. So I'm guessing that what it would do is it would make your covariance, like your 1 sigma error ellipsoid larger, but it wouldn't change your estimate.
Okay.
But yeah, no. So the way I have it set up, because I have my solutions, I don't believe I did that in my solutions, but I think you're right. My gut reaction is that I think that we are supposed to do that, and then I just didn't think about it before. So if that's the case, then thank you for catching my mistake, Justin. But yeah, let's chat about that a bit more on Wednesday.
All right. Sounds good. Thanks.
Thank you. Yeah, that's a really good question. All right. Other generic questions, or is it all specific questions now? By which I mean, like, would our discussion benefit everybody, or is this like just you want my attention essentially on a one-on-one thing? All right, cool. Sounds like we're good on generic stuff. So I'll stop the recording. Hopefully this recording benefits everybody that's trying to get homework 2 finished up. And then we will chat about this more in office hours on Wednesday. And office hours might have to run a little bit late on Wednesday because I recognize that it's, the last office hours before the homework is due. So I'll do my best to stick around later if time permits. But yeah, thanks for coming, everybody. I'm going to stop the recording now.